Hello, my name is Bora from 10J. In this video, I'll be talking about geometry and subtopics. Come on, let's start. So, what is geometry? Geometry is a branch of mathematics that deals with the measurement, properties, and relationships of points, lines, angles, surfaces, and solids. So, we said that geometry is a branch of mathematics, but geometry also divides into two. We can divide geometry into two, like plane geometry and solid geometry. First, plane geometry. Plane geometry is about flat shapes like lines, circles and triangles, etc. Shapes that can be drawn on a piece of paper. They are everything that you draw in your notebook or in your everything that's drawn on your textbook. They're in plane geometry. On the other hand, solid geometry. Solid geometry is about three-dimensional objects, like cubes, prisms, cylinders, and spheres. So solid geometry is the type of stuff we see on everyday basis. We've said that geometry divides into two, plane and solid geometry. And we already said that plane geometry consists of two-dimensional shapes and solid geometry consists of three-dimensional shapes. But that doesn't end there. Geometry is a very complex and full branch of mathematics. It has a lot of subfields. And these subfields, we use it every day. We don't notice it, but we do. And they're very helpful. We have some of them right here. Algebraic geometry, differential geometry, topology, and Euclidean geometry. But what are they? So first, let's start with algebraic geometry. Algebraic geometry is a branch of mathematics classically studying zeros of multivariate polynomials. Modern algebraic geometry is based on the use of abstract algebraic techniques, mainly from commutative algebra, for solving geometrical problems about these sets of zeros. So let's look at some real-life applications of algebraic geometry. Actually, algebraic geometry is used in a lot of areas of robotics and mechanical engineering. For example, it is important to the development of CAD systems, think NURBS, computing intersections of primitives, etc. And AG stands for algebraic geometry, comes up in robotics when it is important to figure out, say, what motions a robotic arm in a given configuration is capable of, or to construct some kind of linkage that draws a prescribed curve. After the algebraic geometry, we have topology. Topology is a bit different than other types of subfields of geometry. Topology is concerned with the properties of space that are preserved under continuous deformations, such as stretching and bending, but not tearing or gluing. This can be studied by considering a collection of subsets, called open sets, that satisfy certain properties, turning the given set into what is known as a topological space. Important topological properties include connectedness and compactness. But where do we use them in our real life? In our real life, we use topology in movement planning problems, like giving a robot how to move it from point A to B efficiently without knocking everything over and or falling on its face. Think about how much coordination your arms and legs have to dance a ballet dance, for example, and think of how you would program a robot to do it. So basically, we use topology to write algorithms for robots, such as algebraic geometry. After topology, we have Euclidean geometry. Euclidean geometry is probably one of the most known of them all and one of the most used of them all. But what is Euclidean geometry? Euclidean geometry is a mathematical system attributed to the Alexandrian Greek mathematician Euclid. Euclid's method consists in assuming a small set of intuitively appealing axioms and deducing many other propositions from these. Although many of Euclid's results had been stated by earlier mathematicians, Euclid was the first to show how these propositions could fit into a comprehensive deductive and logical system. So, we talked about plane geometry, solid geometry, algebraic geometry, Euclidean geometry, topology, but the main idea, the main part of the video was elliptic geometry. Maybe it's not important as Euclidean geometry, topology, or algebraic geometry, but it's also a subfield of geometry which humans been using it for multiple things throughout the history. So what is elliptic geometry? Elliptic geometry is a special type of Riemannian geometry, which is another very special and useful geometry type. Elliptic geometry is a non-Euclidean geometry, which means that there are no parallel lines. This geometry is usually thought of as taking place on the surface of a sphere. We said that all lines are parallel because the lines are great circles in this geometry, and the points are pairs of diametrically opposed points. As a result, all lines intersect in elliptic geometry. As an example, in which given a line L, let this be our line L, and the point P, outside L, there exists no line parallel to L passing through P. So as you see, it must pass through P. And if it passes through P and is out of the L, it can't be parallel. There is no way that they can be parallel. That's why we say that it doesn't have any parallel lines. So in order to achieve a consistent system, however, the basic axioms of neutral geometry must be partially modified. Most notably, the axioms of betweenness are no longer sufficient, essentially because betweenness on a great circle, which is a line, makes no sense. Namely, if A and B are on a circle and C is between them, then the relative position of C is not uniquely specified, and so must be replaced with the axioms of subsets. And here, an axiom is, in mathematics, a proposition that is assumed without proof for the sake of studying the consequences that follow from it. It literally means evident truth that requires no proof. So if we combine all what we've said that there are no parallel lines in elliptic geometry, and we said that it's a special version of Riemannian geometry, and all the other stuff, we'll see that in any triangle in an elliptic geometry sphere, we'll see that the sum of the angles for this triangle, C, alpha, and beta, their sum will be bigger than 180. And this is a result of lines being great circles and uh, they can't have any parallel lines. They intersect everywhere all the time, and they intersect even though they're parallel. When they're vertically, they intersect always in the poles, and this is a result of them. So none of the triangles can have 180 sum of angles in an elliptic geometry. This also proves or gives another reason why it's not an Euclidean geometry. Because in Euclidean geometry, all the triangles have 180 sum of angles. Their sum of angles in Euclidean geometry is always 180. So we said that on a sphere, on an elliptic geometry sphere, the sum of the angles in a triangle is bigger than 180. And we said that that's because there are no parallel lines and they cross each other all the time, and the lines are great circles. But the actual reason why that occurs is that on a sphere like world or earth, the space, the surface of the earth or a sphere is not Euclidean space, and that causes the sum of the angles in a triangle to be bigger than 180. But locally, the laws of the Euclidean geometry are good approximations. In a small triangle on the face of the earth, the sum of the angles is very nearly 180, but still not 180. I hope you liked it. I hope it was informative. And I hope I get a good grade. Say that, teacher.